All right, guys, welcome to the first Aero Lab. Obviously, there's a little bit of the first 2 weeks of this semester, a little bit cut short on lab time for you guys because of MLK holidays, and then the first day we didn't want to do the first lesson to be the lab lesson because there needed to be a little bit more intro. But we're excited about this year's version of 2000. At least I'm excited about this year's version of 2004 because it's the only one I've seen. Lab. We're going to try some new things this semester. You guys are a little bit of a guinea pig course, but obviously that's a good thing. You guys are going to get to try out some new things and spread your wings a little bit, right? We talk a little bit about getting to the point where you guys work on open-ended problem sets, nothing where there's a fixed, is it right, is it wrong kind of answers. And you're going to get to do that in the design portion a little bit more so than you probably got to, whether it be in the balloon lab or anything else. It's going to be a bigger palette for you guys to play around with that. And we'll see how it goes. How well you guys do in this lab basically depends if next year we do it again. So welcome for all that. So you saw some of this stuff yesterday, but I've added to it based upon who we have here. So I've added on here the lab sections where you can see the TAs and CAs have signed up to kind of consistently be here. So you'll know kind of who your folks are to ask questions for. Obviously, you can ask questions of any of the folks, but they're accessible here in the lab time. So please use them. Or LA. So LA is hugely important because these are the consistent faces you're going to see in all your labs. They're going to help you through this whole process. They've done this before, relatively recently, although not this specific lab. They've been working with us on developing it, so they've got a lot of good insight to go with. So you guys want to introduce yourself?
Hey guys, Chris Brown. I recognize a lot of your faces from last semester, and I look forward to working with you guys again.
Red glasses, Venus. That's my only tip for you guys. I'm gonna mess it up consistently. But great team, and then you can't avoid the.
Yeah, I just figured everybody already knows me, but yes, yeah. Trudy Schwartz. I'll be doing the lab for 2004 this year, so I'll be there for all the lab sections and helping you out with this new lab. I'm pretty excited about it. And the lab assistants are really excited. They're like fighting over who gets to work on this lab. So if that tells you anything, I hope that's a good sign.
So Trudy's our adult in the room. She's going to keep us from doing anything too stupid with this lab because it is a little bit of a like I said, new thing. Safety first. All right, dropping my pen. All right, so we talked about this yesterday. So this is your lecture flow for this year for 2004, right? Aerodynamic concepts, 3D wing, whole aircraft drag, performance, stability, and then propulsion. All right. So overlay on top of that, this is how the lab is going to integrate with it. So we're going to try to make sure the lectures integrate well with what you're having to perform in the lab. It's a little bit tough because of the timing, but we're going from lecturing yesterday on 3D finite wing concepts to actually doing those 3D finite wing concepts on an airplane as part of the lab. Next lesson, I'm going to talk whole aircraft drag, and then we're going to go talk and do whole aircraft drag for an aircraft in this lab. Now, you'll do a little bit more expanded work than we're going to talk about in the lecture because there's just more time here. And we're going to actually delve into a little bit more of some of the conceptual design techniques that people use to estimate some of the values that in Anderson he's just going to give to you and say, hey, this is your zero lift drag coefficient. Because most of the time those values are determined experimentally. And obviously we have some limited experimental resources here, but we don't have too many, so we're going to use design techniques to estimate them going forward. So the first lab you're going to do is computational aerodynamic performance of the Tempest UAS, and we'll talk a little bit more in detail as we go. This is just the overview. This is basically the first 3 weeks of the course only, right? So lab 1, whereas the lectures are kind of heavily biased before exam number 1 of being all the aircraft performance and aerodynamic concepts, the labs are kind of flipped. Your first lab is actually much shorter. It's only 3 weeks long to give you a much longer time on the back end for the fun stuff. All right, and that's what we want to get to anyway, so why not? And that's this. So Air Design Lab number 2 is basically a from-scratch design of a glider, right? And you may be thinking, well, glider's a toy. That doesn't take that long to do. If you do it right, it does. And if you do it from an engineering perspective, it does. You could obviously develop a toy glider. My kids do it all the time. Granted, they crash a lot. But as an engineer, I don't expect you to crash that first flight, right? First flight crash is bad. Generally, first flight crashes mean your whole program gets canceled. So you're going to do it from a standpoint of an engineer, and your first flight, you're going to be confident. You're going to stand up there, you're going to chuck that thing, and that beauty's going to fly, hopefully the first time out, because you've done the work on it. Okay? So that's the difference in terms of what we're doing here. So glider design, build, fly. We're going to take everything we do for this first lab. So everything you're doing in the first lab carries over. For that reason, teams aren't going to change from lab 1 to lab 2. So what you're basically doing up here is building the tools so that you can do this. The one add-on on the second part is that we're going to make sure you understand the basic concepts of stability, so that even though your aircraft has a great wing, it has the lift necessary, has a great L over D, so it predictably has a good range. If you throw it and the thing stalls immediately and then does a death spiral into the ground, obviously you're not getting very far with that airplane. So you need to have some basic understanding of stability control, be able to estimate that for your airplane and make sure that when the first time you throw it, it at least in general is stable. And there's always going to be some wiggle room there. We'll talk more about that for the design lab when we get to it. But you can see it kind of lines up, all right? So we're going to talk range and endurance by the end of next week. That gives you another week to basically get that information, digest it, put it into the concepts of what you're doing for the lab turn into one. Going to do a few other things in terms of performance, but right after exam 1, we're going to hit stability, and that'll hopefully get that kind of just in time for you guys to look at your conceptual design for the glider and adjust it appropriately based on stability concerns. All right? So general flow makes sense, hopefully. This is kind of what we're trying to do from a pedagogical or learning standpoint, what we're trying to teach you from an engineering thing, big picture, right? Obviously, we want you to learn the concepts of general air vehicle design and performance, but also what you need to be thinking about is, what does this mean in terms of the different steps I take as an engineer through a general project design of any sort? And you'll use this when you get to senior design, you'll use this out in industry as well. But basically, lab 1 covers conceptual design, so back of the napkin, paper design, thing that is easy to do, it's cheap, there's not a whole lot of risk involved, and it gets you very quickly to converge on a general region of a design space, right? Get me in the ballpark. Computational analysis, you're going to get exposure to. You're not really going to do. So what we're going to provide you is CFD data of an airplane, and you're going to be able to compare. Hey, my conceptual calculation said this. Here's the CFD data. It's not truth data, but it's more refined data. Compare and see how well my kind of back of the napkin calculations do to something that it takes a little bit more time, a little bit more resources, but is also somewhat low risk. And then when you get into this phase, we're going to expose you to experimental. And not experimental, so you've already seen experimental data when it came to putting something in a wind tunnel. And putting something in the wind tunnel costs a lot of money, generally takes a lot of time, but it is minimal compared to the cost, time, and risk associated with flight tests. And so what you guys are actually going to do is experimental relative to flight test. And granted, your cost isn't going to be nearly as much as what it costs someone out in industry to do flight tests, and the risk isn't nearly as high, but you're going to get a feel for that. You're going to feel for what it gets you, what it doesn't get you, and the amount of preparation required to do good flight tests is well above a lot of these other steps that we're talking about here, right? It doesn't cost a whole lot of money to sit in front of a computer, run a CFD program. You know, if it fails, okay, it fails. I got a lot of time to debug it, but there's no real damage, right, being done. A lot more damage being done here. And one of you guys will have a horrific crash. Probably more than one of you guys will have a horrific crash that is, unrecoverable. But that's, again, that kind of hammers home kind of where we're getting at. If you do your job well conceptually and computationally, hopefully by the time you get to flight test, everything is boring. You know how that thing performs, and it behaves correctly, and everything goes well. All right, but there's always a lot of uncertainty there. So we want to expose you to that, because when you get to senior projects, you know, if you're working on building a UAV in support of something else, this wind tunnel is not going to support you doing in-depth testing. You're going to have to do flight tests. Right? You're going to have to do a lot of flight tests to get the data you need. And so we want to expose you to that up front. All right. So questions on the overall flow, on how that's going to work throughout the semester? Good? All right. Some more details on this. So we're going to focus in on this part, but I did want to give you an overview of what you're doing for part 2. There's still some things in the flux of that development, a lot of things. But for weeks 1, 3, the team effort and deliverable, All right, we'll talk a little bit more of that later. You're going to develop basically your tools. All right, I'm going to develop my tool sets to do analysis and error. For conceptual designers, we call this benchmarking. Right? So you never want to go in to any sort of design project and blindly use tools and equations that you have no idea what they do. You have no idea the assumptions behind them. You have no idea how they were developed, and as a result, you have no idea what the uncertainty is in terms of what you're developing. So what typically you'll do is you'll take your tools and you will plug in a known answer, right? And you're going to see what the output is. And if the output is well off of the known answer that you have, then you have problems with your tool set, or you're using the tools outside of the bounds for which they were developed, right? If I have, and you see this a lot, because a lot of design tools are built off empirical data, things that come from industry and actual testing of real airplanes. And so what they're doing is doing curve fits to data for like aircraft. And so if you use an aircraft that is hugely dissimilar, because a lot of the design tools, if you've got a design tool that was built off of data that is based off of supersonic jets, from 1980 on, and you're trying to build a glider with it, it may not give you the answer you want, right? Because there are different assumptions that roll into it. So it's always important to understand what your tools give you. It's not a black box where you just throw in data, it spits out an answer, and you believe it like it's the truth, okay? So what you're going to do in this first half is benchmark your tools. The equations you learn in your lecture are your tools, all right, in terms of how to design it. And you're going to do that against a known, which is the Tempest UAS, all right? Once you benchmark that tool, you're going to analyze the finite wing, the drag polar performance analysis, and brief those results to the lab team. All right, so your deliverable on the first one is the team report out saying, this is our lab results of what we got from our conceptual equations, this is what the CFD says, this is the difference, this is what we think about that difference. Okay. Once you're done with that, and you feel confident in your tools, you're going to take those same tools into the second part of the lab. Individually, everybody individually in the team is going to design their own glider. All right. And you guys are going to have an internal team fly off. Not really flying it, unless you want to build something and fly it. But you're basically going to look at the data that everyone has done and compare performance and see which design has the performance that you want to meet the requirements. The reason why we're not changing teams is I want you to use the same tools you built, and I want everyone in the same team using the same tools. Otherwise, the comparison might be a little bit off, right? So you're going to design 5 to 6 different designs. Then you're basically going to compare them all, score them all, and say this is our winner for our initial risk reduction. This kind of lines up with the PDR. I'm calling it more conceptual design review because you're not doing enough iterations to really kind of get a risk reduction, right? Really what you're doing is one step of risk reduction in a preliminary design review, right? But you're going to pick one, and you're going to say, all right, that's the basic design we're going to start with, and now we're going to tweak that one design and build it, and that's the one we're going to fly for the competition, okay? So do that. And then the second half of it, you'll do a really quick tabletop briefing that's going to be worth points. Granted, basically within this, we're just going to come to your groups individually. You're going to step us through your designs and tell us how you scored them and why you're picking the one you're picking. From that, after you've done that, you pick your one. Your whole group is going to build that one plane. You're going to modify it based on the requirements for stability that you feel like you need to do. You're going to continue to work on it and tweak it, and then you're going to build it. This is going to happen really quick, right? We're not talking a real complex build, and this is where all the lab team is really going to be very helpful in helping you guys kind of get to a quick build that is of a good enough quality. And then you're going to fly it. That's on a weekend, by the way, 2 March. Tentative still, we may change that slightly. You're going to fly it, and then you're going to collect data off of that, and then you're going to brief your final report. Now with conceptual information, no computational, because we're not going to, unless you could do it, and that would be obviously pretty cool if you did, and compare it to your experimental data that you collect off the actual glider. All right? So that's the layout for the whole Aero lab from start to finish in terms of going forward. The schedule lays this all in more detail, so please look at that. Make sure if you're looking at time schedule, again, remembering that's a Saturday, look at your schedules ahead of time, and you're making sure you're planning ahead to be at those events. Okay? As we go forward. And it gets really, like I said, it gets a little crunch towards the end here. So be prepared. That's going to be a little bit of a helmet fire, as they say, going into the last couple of weeks of the Aero side. All right. So what aircraft are you benchmarking? You've probably seen this airplane all over. There's pictures of it all over the aerospace department. This is the Tempest UAS, built to basically do atmospheric research locally here at CU. And you're going to analyze it. All right. it's your known. You're going to say what is it? And we talked a little bit yesterday. We had a little bit of fun with the ground effect airplane, the Caspian Sea Monster. By the way, anyone watched that video? Unfortunately, I had to rush through that going for it. It's a really cool airplane, by the way. You guys really should look at that video and look at it. But we're going to continue that theme because what I'm telling you now, all this benchmarking, in engineering, it's called benchmarking. In the world I came from, it's called intelligence analyst, right? If I see a new airplane flying out there at an air show and I want to know how it performs, I'm doing the same things you're doing here, okay? So after you leave here, you should be able to look at any airplane and do some basic assumptions and get a basic performance capability of that airplane based on its geometric shape alone, all right? It's a really cool skill set to have. Very quickly being able to analyze and say, that airplane, it should perform like this, roughly, within 10 to 20%. And get a good sense of performance without knowing anything else about it going forward. So that's basically what you guys are doing. So if you do that airplane, you can do this airplane. This is the UK Tempest. So two different Tempests, but same concepts and procedures. Now obviously, supersonic aircraft, there's some additional things that you would do with that, but in general the concepts are the same. And you can learn the additional methods to do supersonic flight if you take Dr. Darren's class with aircraft design or anything else. And get in further detail with this, but understand that the skills you're going to learn are transferable. Just because we're doing a small UAS doesn't mean you can't start looking at a bunch of other airplanes out there, okay? Again, there are some differences with supersonic, but in general, you can determine subsonic performance for this very much the same as you would do for the glider, all right? This is some more detail on it, and you're going to need to know the important thing is understanding that the shape of the airplane dictates a lot of what it does, right? That should not be a shocking surprise for anybody that the shape of an airplane dictates its performance, all right? That's why detailed understanding of the shape is important. And then you'll be provided this information, and you're going to do some approximations based on just a basic drawing. And again, kind of simulating intelligence work, sometimes all you have is a picture of an airplane. And that picture should be enough for you to generate some good performance or basic understanding of what it does. Right? Learning objectives, we've been kind of hitting on this throughout the whole discussion here. So we're going to reinforce what we learned in lecture. That's kind of the whole point in labs anyway. We're going to be able to do the benchmarking against the CFD and understand how well our conceptual equations match the more high-end computational stuff. Understand the limitations of both. Right? So you're going to be able to speak to, well, this is why I think my conceptual theoretical calculations didn't match. Here are the limitations I exceeded. Here's where the approximation is good, and here's where I shouldn't use the approximation in different flight regimes. And that'll help you understand kind of what you're getting out of the tools that you have. Obviously, we're going to become familiar with the CFD and limitations. Maybe we should get a guest speaker on that. But maybe we'll pull in somebody with more CFD background and give you some understanding of that. And then enable the informed use for your next lab, which is what we've been kind of talking about as we go forward. All right, deliverables. Obviously, we want you to be here. If you're not here, you're not getting the work done. The time you have in lab is really just set aside time for you and your team to get together and work on this. It is not, 3 weeks is plenty of time to do the initial benchmark. After the first week, you could do 85% of the lab, right? After the first week of lecture. So you can really get ahead of this and start being a little bit more creative and think through a little bit more different things if you want. Your team presentations will be on 4 February during your lecture period. We'll set up basically very similar to 2002 design presentations where we have 2 rooms. You guys will sign up for a time during your section, and then you'll provide that briefing, 10 minutes plus 5 minutes of questions. Section 6 of your handout, which is posted to Canvas right now, if you go look in the lab section, has all the requirements, the detailed requirements of what questions you need to be able to answer, what plots you need to be able to show and describe to us during that time. And then you need to upload both your slides and your calculations, so your tools, basically, in terms of what you're going to do to use it. And I'm not limiting it. You can use MATLAB. You don't have to use MATLAB, although obviously that's one of the primary tools of choice for the department and engineering in general. So I encourage you to use it if you want to get better at it. But if you want to, you can use a spreadsheet. It's just as valid, or handwritten calculations. But I would kind of push you away from handwritten calculations just because you want to be able to do these calculations repetitively and iterate over designs. So you don't want to necessarily have to be doing it by hand every time. All right? That's just for you a time saving. So build your tool, preferably a software tool, that then you can reuse down the road. All right. Questions on deliverables for this lab? All right, so what's your task for today? Select your own lab groups. So we aren't changing lab teams. This is something that, from a design standpoint, you need to have consistency going from developing your tools through the whole process. So we're going to allow you to do your own teams, and it's going to be done in a Canvas sign-up. So who here has done that before? Canvas sign-up for teams? Because I haven't. Okay. So if you go into Canvas, and I'm going to actually pull it up because.
I have it here if you want to switch.
Oh, you have it over there? I've got it right here. That's good. If you go into Canvas, there's the course. If you go to People, because that's who you are, and Arrow Lab Groups, you're going to see a bunch of groups on to the right with no people in it, right? By section. So section 11, which is this morning, you have up to 11 teams, all right? 5 to 6 a team, no less, no more. Okay? We can't have too many groups, right? There's only so much limit we have to be able to have time to get all your briefings in during your lab section. So you need to fill these all out. I'm going to give you time to kind of converse, talk, think about schedules. All right, getting together, think about skill sets, right? But try to get that cohesive team in terms of getting together. Again, this is something you'll do down the road anyway for senior projects, so you might as well start talking about interests and background and things like that, get to know each other a little bit. Fill those out by the end of the lab period. And then before the lab period is over, we'll take a look and see if there are any remaining kind of slots to be filled, still some uncertainty, and we'll start figuring those last bits out, okay, over the last 30 minutes or so of class. All right, so that's your first priority. Second one, obviously download and read the handout and get a sense of the full scope of what you're doing, okay, and become familiar with that. And then from there on, you guys are off and running, okay? Every other lab up until that presentation is you working on these projects. We'll have a couple of probably short lectures over the next couple of labs to talk about a few more of the details design-wise that we may not get to in class. We may, but other than that, you guys are pretty much cut loose to do that during your lab sections. All right, so we want to do that. Questions? Trudy, you got anything?
From my perspective, I'm going to mostly be helping with lab logistics, the scheduling, and also helping you with any questions that you have. When it comes to the aircraft theory and the specifics of this lab, I'm new to it as well. So I'm excited to learn with you. And that's why I really pulled in the lab assistants. I want to give a little plug to Chris Brown. He's done a lot of work in Recov with Iris, so he's actually really familiar with this aircraft. So good resource for you. And then Venus and Rowan did a similar version of this lab last year. So they also have some really good insights to this lab, although they didn't get to build the glider like you guys do. So this is a different version of what they did, but they have some familiarity with the CFD results that came from the Tempest aircraft. So good resources that we have for you to help in this lab, and I'm excited to get started on it.